50 light-years away, orbiting a red dwarf star so fast that its year lasts 11 hours, there is a planet. It has no air, no water, no clouds, no weather of any kind. One side of it bakes in permanent, unrelenting starlight at temperatures approaching 1400 degrees Fahrenheit. The other side sits in permanent, absolute darkness that has not seen light in billions of years. The surface is covered in dark volcanic rock, ancient and barren, pocked by micrometeorite impacts accumulated over geological timescales, with no plate tectonics to recycle it, and no water to erode it, and no atmosphere to protect it from the constant bombardment of space. We know all of this because 2 weeks ago, for the first time in the history of science, the James Webb Space Telescope looked directly at the surface of a planet beyond our solar system and read what it was made of. Not the atmosphere, not the space around the planet, the surface itself, the actual rock, 50 light-years away. Let me tell you why that is one of the most significant things humanity has ever done with a telescope, and why the specific answer that came back, a dark, hot, barren rock devoid of any atmosphere, is in some ways more scientifically valuable than if we had found something warmer and more promising. The planet is called LHS 3844b. It was discovered in 2019 orbiting a cool red dwarf star in the constellation of Indus. It's classified as a super-Earth, meaning it is larger than Earth but smaller than Neptune, roughly 30% bigger than our planet in diameter. It is tidally locked to its star, the same way our moon is tidally locked to Earth, meaning one hemisphere permanently faces the star and the other permanently faces away. It completes one full orbit every 11 hours. At that distance from its star, the dayside temperature reaches approximately 725 degrees Celsius, hot enough to melt lead, hot enough that if there were ever an atmosphere, it would have been stripped away long ago by the stellar radiation at that proximity. The team that observed it was led by Laura Kreidberg of the Max Planck Institute for Astronomy in Germany. They used JWST's mid-infrared instrument, called MIRI, to observe the planet during what astronomers call secondary eclipses. These are the moments when the planet passes behind its star from our perspective. By measuring the total infrared light coming from the star plus planet system just before the planet disappears behind the star, and then measuring the light from the star alone while the planet is hidden, you can subtract one from the other and isolate exactly the light coming from the planet itself. Not reflected starlight, the planet's own thermal emission, the heat radiating from its surface. This technique sounds simple, and it is simple in concept. In practice, it requires an instrument sensitive enough to detect the thermal signal of a planet 50 light-years away against the overwhelming glare of its star. It requires the patience to observe 3 separate secondary eclipses across 2023 and 2024 to accumulate enough photons to build a reliable signal. And it requires the ability to translate a specific pattern of infrared wavelengths into a geological composition, the way a forensic scientist reads a fingerprint. JWST can do all 3 of those things. No telescope before it could. Here's what the data showed. The infrared spectrum of LHS 3844b's dayside surface does not match an Earth-like crust. On Earth, the continental crust is dominated by silica-rich rocks like granite. These rocks form through processes that require water. Water drives plate tectonics. Water allows lighter minerals to melt and rise through the crust over geological time, creating the mineral composition we stand on. The presence of granite-dominated crust is, in a real sense, a signature of a planet that has or had liquid water at some point in its history. LHS 3844b shows none of that signature. When Kreidberg's team compared the observed infrared spectrum against libraries of known geological materials from Earth, the Moon, and Mars, the Earth-like granite crust was ruled out clearly and definitively. What the data does match is basalt, dark volcanic rock rich in iron and magnesium. the same material that covers the lunar Maria, the dark plains on the moon created by ancient lava flows, the same material that forms the ocean floors on Earth, the same material that covers the surface of Mercury. Basalt is the rock you get when you have a rocky planet with volcanic activity but no water-driven recycling to transform it into lighter, silica-rich continental crust. It is the geological signature of a world that formed hot and stayed geologically simple. The study's lead author, Sebastian Ziba of the Center for Astrophysics and Harvard and Smithsonian, put it directly. This planet likely contains little water. Not probably never had water, not might lack water. Likely contains little water. That phrasing matters. It is the careful, precise language of a scientist who has looked at what the data says and is telling you what it shows without overstating the certainty. What the data shows is a surface composition inconsistent with the water-driven geological processes that would indicate the presence of substantial water now or in the planet's geological past. There is an interesting complication in the data that points toward an active geological history rather than a completely dead one. The surface of LHS 3844b appears relatively fresh. The basalt signature doesn't show the degree of space weathering, the modification of surface minerals by micrometeorite impacts and radiation that you would expect from a surface that has been exposed and unmodified for billions of years. This suggests two possibilities. Either the surface is relatively young, reshaped by recent volcanic activity that has laid down fresh lava not yet significantly altered by bombardment, or there is some other process actively renewing the surface material. The volcanic explanation is plausible. Tidal forces between a tidally locked planet and its host star can generate significant internal heating through a process called tidal flexing, the same mechanism that drives the volcanic activity on Jupiter's moon Io, the most volcanically active body in the solar system. LHS 3844b, orbiting its star in just 11 hours at very close range, would experience significant tidal forces that could maintain geological activity even without the water-driven plate tectonics that drives Earth's geological cycle. But here is the puzzle. If the planet is volcanically active, where are the volcanic gases? Active volcanoes on Earth release enormous quantities of carbon dioxide, sulfur dioxide, water vapor, and other gases. These would be detectable by MIRI and the planet's atmosphere if they existed. And they weren't detected. No atmospheric signature at all. The team's conclusion is that LHS 3844b is essentially atmosphereless. Whatever volcanic outgassing may be occurring, if any, is not accumulating into an atmosphere. At the temperatures and stellar radiation levels this planet experiences, any gas released from the surface is almost immediately stripped away by the stellar wind. This is what Laura Kreidberg means when she says we see a dark, hot, barren rock devoid of any atmosphere. Not a planet that might have a thin wisp of something. Not a planet with ambiguous atmospheric data. A rock, airless, blasted. Geologically interesting but biologically irrelevant in any framework we currently understand. Now, I want to explain why this finding is extraordinarily valuable, precisely because it found nothing promising. The search for life beyond Earth, the project that drives much of the scientific motivation behind JWST's exoplanet program, requires not just finding worlds that look promising. It requires developing the ability to distinguish promising worlds from barren ones, to read the geological and atmospheric signatures of distant planets well enough to sort them into categories, worlds that could plausibly support life as we understand it, worlds that definitively cannot, and worlds where the answer is ambiguous enough to warrant further study. Without the ability to make those distinctions, the search for life is not a scientific program, it is a lottery. You point your telescope at a planet and hope. What JWST has just done with LHS 3844b is demonstrate for the first time that we can actually make those distinctions. We can look at the surface of a rocky planet 50 light-years away and determine what it is made of. We can compare that composition against known geological processes and determine what kind of planetary history produced it. We can rule out the geological signatures that require water. We can identify the volcanic rock signatures that indicate a waterless, airless world. We can, in other words, read the geological story of a planet we will never visit from the light it emits across half a century of empty space. That capability applied to LHS 3844b produced the answer barren rock. Applied to a different planet, one with a thicker atmosphere and a surface composition that requires water to explain, it might produce a very different answer. The instrument is working. The technique is validated. The question of which planet to point it at next is now the most important question in exoplanet science. Here is the broader context that makes this moment even more significant. Exoplanet science began in 1995 with the first confirmed detection of a planet orbiting a sun-like star beyond our solar system. That first planet, 51 Pegasi b, was a hot Jupiter, a gas giant orbiting extremely close to its star. We knew it existed from the gravitational wobble it induced in its star. We knew almost nothing else about it. In 1995, the idea that we would one day look at the surface of a rocky exoplanet and determine its mineralogical composition from its thermal emission was not a realistic scientific goal. It was a wish, something researchers put in the long-term vision sections of grant proposals as a marker of where the field might aspire to be in some distant future. That future arrived 2 weeks ago. 30 years after the first exoplanet detection, we are directly analyzing the geology of worlds 50 light-years away. The pace of this progression, from detecting the gravitational wobble of a planet to reading the rock type on its surface in 30 years, is extraordinary by any historical standard of scientific progress. Sebastian Ziba said something in the announcement statement that I think deserves to be taken seriously as a description of what JWST is enabling at a methodological level. He said this kind of deciphering the geological properties of planets orbiting distant stars is the next step in unveiling their nature. The phrase geological properties is the key one. We are not just detecting planets now. We are not just measuring their masses and orbital periods. We are characterizing their geology, their mineralogy, the processes that shaped their surfaces over billions of years. We are reading their histories in the light they emit. The comparison to Mercury in the scientific paper is deliberate and informative. Mercury is the closest planet to our Sun. It is airless, heavily cratered, covered in dark basaltic plains, and geologically ancient. It has no plate tectonics, no water, no atmosphere to speak of, and surface temperatures that range from extremely hot on the sunlit side to extremely cold on the dark side, though nothing as extreme as LHS 3844b, given the tidal locking that creates permanent hemispheres rather than a day-night cycle. When scientists say LHS 3844b resembles Mercury, they are offering the clearest visual and geological reference point available in our solar system for a planet that is definitively not hospitable to life, and whose surface composition reflects a geological history completely unlike Earth's. But Mercury is also scientifically interesting on its own terms. Its unusual density, its magnetic field, its volcanic history are all active areas of planetary science research. A Mercury-like exoplanet 50 light-years away is not interesting because it might harbor life. It is interesting because it represents a class of rocky planetary object, the airless basaltic tidally locked hot rock, that may be extremely common in the galaxy, and that we now have the tools to characterize directly rather than inferring from orbital and mass data alone. Think about what the solar system looks like in terms of rocky body diversity. Mercury, Venus, Earth, Mars, the moons of other planets, asteroids of various compositions. Each of these objects tells a different story about how rocky planetary bodies form and evolve under different conditions. The solar system is our baseline, but it is one data point, one solar system, one set of conditions, one outcome. To understand the full range of what rocky planets can be, what geological histories are possible, what surface compositions arise under what conditions, we need to study rocky planets in other systems, formed around different stars at different distances under different irradiation conditions. LHS 3844b is the first direct geological data point beyond our solar system. it will not be the last. The JWST program continues to observe rocky exoplanets in the TRAPPIST-1 system, 7 Earth-sized planets orbiting a red dwarf star approximately 40 light-years away, at least 3 of which are in the habitable zone where liquid water could theoretically exist. The TRAPPIST-1 planets have been among the most studied exoplanets since their discovery, but their small size relative to their star makes atmospheric and surface characterization extremely challenging, even for JWST. The techniques validated on LHS 3844b, the secondary eclipse method applied to rocky planet surface emission, will be applied to the TRAPPIST-1 planets as JWST accumulates more observing time on those targets. What comes out of those observations will either be the most significant scientific finding in human history, or it will be another lesson in what rocky planets look like when they lack the conditions for life. Both outcomes advance the science. Both outcomes are worth the investment. Because the question we are asking, is there life elsewhere, is important enough that we need the answer, whatever it turns out to be. And for the first time, we have an instrument good enough to actually look. Here's what I want you to take away from this story that the headline doesn't convey. The planet LHS 3844b is not interesting because it might be habitable. It is almost certainly not habitable by any framework we currently understand. It is interesting because studying it required developing a capability that has never existed before in the history of science: the capability to directly read the surface geology of a rocky planet beyond our solar system from the infrared light it emits. And that capability, once developed and validated on a world we are confident is barren, becomes the tool we use on worlds where the answer is not yet known. The dark, hot, barren rock 50 light-years away is not the destination. It is the proof that the instrument works. It is the validation of the technique. It is the first chapter of a story that ends somewhere in the decades ahead with an answer to the most important question our species has ever asked. Are we alone? JWST just demonstrated that it can read what another world is made of from 50 light-years away. The next step is pointing that capability at a world where the answer might be something other than barren rock, and we are already doing that. The observations are running, the data is accumulating, and somewhere in the photons that JWST is collecting right now from planets we haven't fully analyzed yet, the answer may already be waiting. 3 takeaways. 1. The James Webb Space Telescope has for the first time directly analyzed the surface composition of a rocky planet beyond our solar system using thermal emission from the planet's own surface rather than atmospheric transmission. This is a methodological breakthrough that changes what exoplanet science is capable of. Not the detection of planets, the geological characterization of their surfaces. 2. LHS 3844b is a dark, airless, basalt-covered world with no detectable atmosphere and surface temperatures reaching 1400 degrees Fahrenheit on its permanently sun-facing hemisphere. Its surface composition rules out Earth-like water-driven geological processes and is consistent with a Mercury-like volcanic history. It is definitively not a candidate for habitability in any framework we currently understand. 3. The scientific value of finding a barren world is the validation of the technique. A method that can confirm a planet is geologically and atmospherically dead can, applied to other worlds, potentially confirm that a planet has the geological and atmospheric signatures of one that is not. The TRAPPIST-1 system is the next target. The observations are underway. What comes back will either rule out habitability or leave it open. Either answer, arrived at through direct geological characterization rather than inference, represents science at a level of precision that was impossible until this telescope existed. We looked at another planet's surface for the first time. We saw a dark, hot, barren rock, and we built an instrument sensitive enough to know exactly what kind of rock it was. That is where we are, right now, in 2026. Thanks for watching. If this kind of honest, detailed breakdown of what JWST is actually finding and why it matters beyond the headline is what you're here for, subscribe because there is a lot more coming. And I want to hear from you in the comments right now. What do you want covered next? The full breakdown of what JWST is finding on the TRAPPIST-1 system and whether any of them show signs of the atmosphere? the complete story of how we went from detecting the first exoplanet in 1995 to reading the surface geology of one 30 years later, or the science of what a biosignature actually is and what specific signal in an exoplanet's spectrum would constitute genuine evidence of life. Drop it below. Every comment gets read. Whatever gets the most votes is the next video.